All right, so we're at the last chapter, the last section in chapter 4, which deals with optimization. Optimization problems are problems that involve finding the absolute max or min of functions. Common optimization problems include finding area, perimeter, maximizing revenue and profit, and inventory control. Now, of all these problems, the ones that will probably make the most sense are maximizing revenue, maximizing profit, minimizing costs. That, there's that business aspect to it. But you can also maximize area. You can also maximize perimeter. You can also work on your inventory control. So I'm going to go through a plethora of different problems, but you're going to probably connect more with some than with others. Okay. So this one says, what are the dimensions of a rectangle with an area of 225 and that has the least perimeter? So we're going to do this first example and understand that I read it, but you may be like, wait a minute, what does this have to do with Extrema? We're trying to find the least perimeter. That's minimization. If you're trying to maximization, that all it has to do with Extrema. Okay, but the reason why this one's a little weird, let's talk about it. Okay, so basically, what do they tell us? They tell us that we have a rectangle. So let's draw a rectangle. Now, with a rectangle, we don't know what the sides are, so we'll call them X and Y. And remember, with a rectangle, if this side's X, that side's X. If this side's Y, that side's Y. Now, remember, they told us something, but they're looking for something specific. So they told us that the area is 225. Well, you remember area is length times width. So when we want to find area would be X times Y equals 225. Okay, so we're going to say that this is given to us in the problem. But that's not the goal. The goal is nothing to do with area. The goal is to get the least perimeter. The least perimeter. The least perimeter. And that clue word of least, that's trying to get at, we're going to do Extrema. Now, all of you remember perimeter is the area around an object, right? So here, if I add up all the sides, which would be X plus Y plus X plus Y, that's going to equal P, which is perimeter. So if I clean that up a little bit, P equals 2X's plus 2Y's, okay? But remember, the goal was to find the least perimeter. It didn't have anything to do with the area. Our goal is to find the least perimeter, which means we need to find the extrema of perimeter. But here's where things get a little weird. I can't. And the reason why I can't is you gave me X and Y. I have two variables. I don't know how to deal with two variables. I only know how to deal with X or Y at this point. So that's when you have to use the given to help minimize the perimeter. Okay, so how am I going to help? Well, you're given X times Y equals 225. Well, we're going to solve for either X or Y, and it doesn't matter which one you do. It doesn't matter which one you do. Let's say we solve for X. So I'm going to divide by Y. We get X equals 225 divided by Y. Now, again, I know you're like, well, what is this all about? Here's why. Currently, I cannot minimize, do extrema, because I got two variables. But if I take the given, manipulate it a bit, and now where there's an X, instead of X, I'm going to put 225 over Y. That little change is the weird part. That's it. So now if you take the given, plug it into the one I'm trying to find the minimize or maximize, now I don't have two variables. So 225 times 2 is 450 over Y plus 2y. Now I'm not dealing with two variables. I'm only dealing with one variable. So that's the weirdness I was talking about for this problem. Now it's up to you. And I'll even give you a hint. So what we're trying to minimize is the perimeter. I'm going to go ahead and rewrite this as 450y to the negative 1 plus 2y. Now we have what we're trying to minimize. Since we're trying to minimize, we're going to do extrema. Extrema means stationary, singular, and endpoints. Keep in mind, I didn't give you a domain, but we can reason a domain, or domain wasn't given, but I'm gonna give you a head start. So there's your equation, stationary, singular, endpoints. There's a little bit of work to do ahead of time, but go ahead and find the extrema of that one. So as we kind of go through this, remember we're looking for stationary, singular, endpoint. So for stationary, we're going to take the derivative. That's going to be negative 450 y to the negative 2 plus 2, and we're going to set it equal to 0. So let's make sure that we got the derivative correct. Then here's our problem again. This is negative 450 over y squared plus 2 equal to 0. Now, when we go to solve this, there are two ways, and I can't do both ways all the time. It's either going to be clearing the fraction or creating a proportion. Both are good, okay? So I'm going to go with clearing the fraction, which means I have a y squared in the denominator, so I'm going to multiply everything by y squared. So y squared over y squared leaves you with negative 450. Y squared times 2 is 2y squared. Y squared times 0 is 0. No more variable in the denominator. You could have also done a proportion, move it over, cross multiply. You'll get essentially the same thing. So I'm going to add 450, add 450. 2y squared equals 450. Divide by 2, divide by 2. Y squared equals 225. Square root, you're going to get two answers, positive and negative 15. Now, the nice thing, you're like, nice about word problems. The nice thing about word problems is we're doing a word problem. And let's say this was in feet. Can you have negative 15 feet? No. So the only one that makes sense in the word problem is 15 feet. 15 feet. Okay. So the nice thing about word problems is it has to make sense. Okay, same thing for singular. When we do singular, you're going to get negative 450 over y squared plus 2. What number would make this undefined? If y was 0, perfect. But can you really have a fence that's 0 feet long? No, it doesn't make any sense at all. So we can already kind of eliminate it on our own, or we can use it. It's just not going to work. It's not going to work. That's the nice thing about word problems is, yes, you're going to get some answers, but they don't fit in reality. Reality is our domain. Okay? Same thing for endpoints. We weren't given any, but in reality, it has to multiply to 225. It all has to add up. So we do have some sort of domain, but we just got to be realistic. It's not going to be 0. And it's not going to be like 500 because you're not going to have one side that's really long and one side that's really small, right? So in reality, endpoints don't make any sense either. So all this work, what do we get for an answer? 15. But we're still going to check it, right? We're going to put it in our calculator. We're going to put 15. We're going to plug it into the original. We're going to plug it into the original. So we have 15. We plug it into the original. So we're going to go to our calculator. Bless you. We're going to go to y equals. We're going to put in our original, which is 450 divided by y, which in this case we'll just put x, plus 2x. And then I'm going to go to the table. We got 15. And when you plug in 15, you get 60. When you plug in 15, you get 60. Okay, so we found that and actually it's y, not x, sorry, y. Y is 15. And the perimeter, which is our answer, is 60 feet. But we also can find x. So what I want you to do is find x as well. Find x as well. So when we go to find x, we go back and we say, oh, right here I can find x. I can use this formula or this formula. I'm going to use this one. X times y equals 225. So we know that x times y equals 225. We already know that y is 15. Divide by 15, divide by 15. What does x equal? Also 15. So if I go back to my original drawing, you find out that every side is 15. So we actually have a what? A square. And all squares are rectangles, but not all rectangles are squares. If you remember all that, okay? And if you add it up, you get a perimeter of 60 feet. So if you want to minimize the perimeter, x and y should be 15 feet. X and y should be 15 feet. So for our second example, it's a little more complicated. Now we're going to be maximizing area. So remember, always focus on the goal. Here, it's maximizing area, maximizing area. So a homeowner has $320 to spend on building a fence around a rectangular garden. Shown in the drawing, 3 sides of the fence will be constructed with wire fencing, which is $2 per linear foot. And the 4th side will be wood fencing, which is $6 per linear foot. So what we have right now are 2 things going on, okay? First of all, I'm going to kind of squeeze it in here. So just to be clear, it's not this one, it's the one before, okay? So to be clear, what are we doing? We are maximizing area. So to be very clear, we are maximizing area. We are maximizing area. And we know just from math, right, that area equals x times y. Everybody good so far? But here's the problem. The problem is I have x and y. I can't do that. So something has to be given. Something has to be given that we can work with. And here's what they said. They said, in addition to having x and y for the area, they're telling us that 3 sides are going to be $2, $2, but the other side is going to be $6 because that's going to be made out of wood. We're doing the previous one. Yeah, so this one is 6, the next one's 8. The matched one is just like another practice, but good idea. Okay. Now, we know that the cost for that is $320. So the total cost is $320. So if you take xy plus 2y plus 2x plus 2y plus 2x plus 6y, that cost is going to be $320. So 2x plus 2x is 4x, 2y plus 6y is 8y, that's $320. So you are given another equation related to the problem, still x and y, but now we're talking about cost. Now we're talking about cost, okay? So I'm going to give you a little head start. And let's go ahead, and our issue is we have x and y, and I can't deal with 2 variables. But remember, the goal is area, not cost. The goal is area. So the focus is on area. I have 2 variables. I can't solve for 2 variables, so I got to get rid of one of them. So what I'm going to do is I'm going to solve for y. You can solve for x or y. Both work, no problem. But I'm going to subtract 4x, 8y equals negative 4x plus 320. Divide by 8, y equals negative a half x plus 40. Negative a half x plus 40. If you prefer decimals, negative 0.5x plus 40 is y. Okay, so again, just like the previous problem, we're trying to maximize area, but the issue is we have two variables. So now I'm going to take y, plug it in for y, and you get area equals x times negative 0.5x plus 40. Little algebra there. Area equals negative 0.5x squared plus 40x. Any questions up to that point? Now that you have the area function, you need to maximize area, which means stationary, singular, endpoints, plug in the table, find the answer. Okay, again, it's that setup that may be the little confusing part, but once we get past the setup, it's stationary, singular, endpoints. Stationary, when you take the derivative, you're going to get negative x plus 40 equal to 0. Is that what we're getting? Okay. Then we're going to go ahead and solve for x. So if I add x, x equals 40. Good so far? Then singular, we look at the derivative. Is there any place where it's undefined or anything like that? None. We're not given any endpoints. We can kind of reason them out, like a really low number, really high number, but those extremes don't generally work. So we have none. So we find that x is 40 feet. Now, if I plug 40 into the original, that is going to give me the area. But another way around that, which we totally can do in a second, but also I can plug the x here. Y equals negative 0.5 times 40 plus 40. Negative 0.5 times 40 is 20, negative 20. Negative 20 plus 40, y gives you 20 feet. Okay, and if I know that, then I know that area equals 40 feet times 20 feet, and I find out that the maximum area that I can get is 800 feet. And if I plug this in here, you'd also get 800 feet, and feet squared when we're talking about area. Okay, so you can find all your pieces just like the last one. Find all your pieces just like the last one. So just to make sure that we're getting clear on everything, I'm going to give you one more example, but to save a little time, I'm going to kind of give you the setup and then we'll talk about it. I'm going to give you the setup, then we'll talk about it. Okay, so let's say you were asked specifically to minimize cost. We're still talking about a rectangle. We're still talking about area and perimeter. We're along those lines of problems. We're still talking about x is one side, y is another side. But you're given the cost to be 8x plus 4y. So the x sides are costing $8 each. The y sides are costing $4 per feet. Okay? But again, what's the problem? The problem is we have x and y. I can't solve when I have two variables. So you have to be given some more information. And you were given that when you take x times y, the area is 1250. When you take x times y, the area is 1250. And that's all I'm going to give you. You got what you want to minimize. You got the given. Your job is to minimize cost, which that clue word means stationary singular endpoints. But now you're on your own. I'm not helping you set up. I'm not doing anything. Just now on you. Find x, find y, and find cost. X, y, and cost. So third one, same idea. And the main idea for these first three problems is what you're trying to minimize has two variables, x and y. I'm not sure how to solve for two variables at this point. I only know how to solve for one. So you have to be given some extra information, and you're going to use the given into whatever you're focused on. So remember, I'm being very clear that we're minimizing cost. The focus is on cost, not area. So I'm going to divide by y, x equals 1250 over y. I'm going to plug in for x. And again, it works either way, whichever one you want to do. I'll do it this way. And then we're going to have c equals 8 times 1250 over y plus 4y. If you did it the other way and you solve for x, it still works. No worries. You get c equals 8 times 1250. 8 times 1250 gives you 10,000. So that's 10,000 over y plus 4y. So now I'm dealing with a cost equation with one variable, not two variables. One variable, not two variables. And if I do stationary, again, what I'd probably do is rewrite this as 10,000 y to the negative 1 plus 4y. We talk about that to make it a little bit easier. And then when you take the derivative to find stationary, that would be negative 10,000 y to the negative 2 plus 4 equals 0, which gives you negative 10,000 over y squared plus 4 equal to 0. Again, same issue. Variable in the denominator. That algebra keeps showing up. How to solve that algebra? Either make a proportion or clear the fractions. To clear the fractions, you're going to multiply everything by y squared, which will leave you with negative 10,000 plus 4y squared equals 0. Add 10,000, add 10,000. 4y squared equals 10,000. Divide by 4, divide by 4. 10,000 divided by 4 gives you 2,500. So be careful. You get y squared equals 2,500. Square root, y equals what? Plus or minus 50, but since we're talking about a length, it can only be 50. So you found your y, but I also need to find x, and I also need to find cost. So y is 50. Again, the singular would be negative 10,000 over y squared plus 4. Singular would be y is 0, but you can't have a length that's 0. Doesn't make any sense. And endpoints would be the extremes. So even if we came up with some numbers on the ends, it wouldn't work, wouldn't be the extremes. So we get y is 50. And then remember, the equations we're given is cost equals 8x plus 4y. And we're also given x times y equals 1250. So I need to find x and I need to find cost. So if I take the y, plug it in for y, divide by 50, divide by 50, x equals 25. And then I now have x, I now have y, which means I now can solve for cost. Cost would be $8 per foot. X, we have 25 feet. Y is $4 per foot, and we have 50 feet. So your cost is going to end up being $400. So if your goal is to minimize cost, you should have 25 feet of X, 50 feet is Y, and your cost, minimized cost, is $400. $400. So let's step away from the side and area and perimeter, and let's talk about revenue. Let's talk about revenue, okay? So this one says, an office supply company sells X permanent markers. So X is number of permanent markers. P is the price per marker. And they tell you P, which is the price, is 10 minus 0.001 X. X is number of markers. So that's given to you. And the question is, what price, so we're going to have to find price, should you charge for the markers? We need to find markers to maximize revenue. So you'll notice I keep on emphasizing what I'm looking for. And the goal for this one is to maximize revenue. The goal for this one is to maximize revenue. Now let's be very clear. The equation that's given, P equals 10 minus 0.001x, is that revenue? No, that is what? That's price. And we know that X is number of permanent markers. So the revenue was not given to us. But we all know from one of the first classes that revenue is going to be price times, I'll put the variables later. But we know that revenue equals price times quantity or times demand. So if you want to find the revenue, you're going to take price. Well, I know what price is. Price is 10 minus 0.001x. And the quantity, I don't know how many, but I know it's X. So we have the pieces to find revenue, which ends up being 10x minus 0.001x squared. So take a minute and notice the revenue was not given to us. The revenue was not given to us. We had to figure out the revenue. We had to figure out the revenue. And now that you have revenue, that's set up, now I want you to do the Extrema. Stationary, singular, endpoints. Notice that no endpoints were given. Make the table. And this one will probably graph. So if you're fast, graph revenue, and you can check it by graphing revenue. Graph revenue, and you can check it. But this ends up being a typical problem where we're trying to maximize revenue or minimize cost or maximize profit. It took a little bit of work to get that revenue, but now maximize revenue. Let me add, I'm sorry about that. Let me add that within there, you could solve for, but I would give it to you. There is a domain. So let's give you a domain because we haven't had a domain in these problems yet. Let's say that your company can only produce between 0 and 10,000 markers. So you do have a domain. Let's make sure you have a domain. It's something you could solve for, but I would give it to you. So the domain is 0 and 10,000. 0 and 10,000. So if we go ahead and do stationary, we take the derivative, that's going to be 10 minus 0.000, sorry, 2 zeros, 0.002 x, set that equal to 0. So you minus 10, negative 0.002x equals negative 10. Divide by negative 0.002, divide by negative 0.002. And if you do that division, what do you get for x? What do you get? 5,000. So in this problem, you get 5,000. That will be our stationary point. So this is recommending producing 5,000 permanent markers. Singular Are there any singular at all? None. There's no dividing. There's no variable in the denominator. There's none. Endpoints, they were given to us. The endpoints are what the company can produce. The company can produce 0, or the company can produce up to 10,000. Now, again, those are possible, just not likely. Just not likely. If you're not producing at all, that doesn't make any sense, or producing at your maximum, you got a lot of stress going on there. Okay, but we'll check them all. So when we go ahead and plug in, our options are 5,000, 0, or 10,000. Okay, so we go to the calculator, and we're going to go to y equals. We're going to plug in the revenue because it's all about the revenue. 10x minus 0.001x squared. We're going to make a really important business decision when we go to the table. If you produce 5,000 permanent markers, you will make a revenue of $25,000. Okay, so 5,000 would give you a revenue of 25,000. If you produce nothing, you will get an amazing revenue of nothing. Now, if you produce 10,000, which is another option, you will get a revenue of nothing. Now, you are a brand new manager with a really important decision. Should we make nothing, or should we make 25,000? 25,000, right? So the idea is we're trying to maximize revenue. Which one gives you the maximum revenue? If you produce 5,000 markers, you will have a max revenue of $25,000. That's the most you can make. Now, let's graph it real quick. I'm not going to be formal about it, but we know when we graph it, X is going to be between 0 and 10,000 because that's the domain. Then as far as revenue, the lowest revenue would be 0. We know that the highest is 25,000, so maybe go up to like 30,000. And again, the window is created around what we need to see. So that's revenue, that's markers. And I know this is really quick sketch, but I really just want to show you the picture that if I go to window, 0 to 10,000 markers, counting by 2,000, and 0 to $30,000 revenue, counting by 5,000s, and we graph that, you could see your revenue going up and your revenue going down. So if we want to maximize it, where's the maximize? On the top. And what do we say the answer was? Second trace, number 1 for value. Type in 5,000, you're on the top. Or because we have the calculator, we could also do second trace. We're looking for maximum, which is number 4. Go to the left, enter. Go to the right, enter. Guess where you think it is, enter. And if you have the graph, which is a great reason why you want to know how to graph, there's your answer staring right at you. So you also have a visual representation that the most revenue you can make is at 0, 5,000. 0, 5,000. So let's talk about one last application. And again, you can maximize profit, you can minimize cost. There's a lot of good applications in here. But what I want to get to, and again, a lot of good applications, is we're going to do example 4. Oops, went too far. Example 4. Oh, that was example 4. We're going to do example, we're going to do example 7. Example 7. Here we go. So this one's a little weird, but let me help you with the setup and then we'll go from there. A management training company finds that at a price of $400 per person, 1,000 people will attend the seminar. For each $5 decrease in the price, an additional 20 people will attend. How much should they charge to maximize revenue? So bottom line, this boils down to maximizing revenue. But the revenue equation wasn't given to us, so we're going to have to do a little bit of work. Now, in order to find revenue, let's agree that if I know the price per customer and I know the number of customers, I will have my revenue. So if I know the price, how much each customer is paying to go to this management training, and I know how many, that will give me revenue. Okay? It's a little weird on how to get there, but here's how we get there. To find the revenue of X, now this is where it's a little weird. Bottom line, I'm trying to figure out, should I give these $5 coupons to people? So X is going to be number of $5, let's call them coupons. Okay, so we know a bunch of people are coming, but if I pass out these coupons for $5 off, will we get more people and will it impact our revenue? So the price per customer, kind of follow along with me, is $400 per person minus the $5 coupon for how many coupons we give. Okay, so not everyone's going to pay the $400. People are going to get that $5 discount. We just don't know how many people are going to get that coupon or how many coupons I should make. And then the number of people, we know that we're going to have 1,000 people there. Plus, we're expecting 20 additional people with the coupon, So I know that's a little weird, and I'd probably help you with that setup. But this represents the price per customer, and this represents how many customers. And if I can multiply those two, we're on our way. But I'm using this as an opportunity to practice your algebra. So that's all I'm going to give you. You need to simplify it. Then you need to do stationary, singular, endpoints. But my concern, and why we're doing this one, is another application and to practice your algebra. If you can't simplify it, you're going to have some issues there. And I will add a domain. That we've agreed within our company that we're only going to do up to 80 coupons. We're not doing any more than 80. So your domain is 0 to 80. Your domain is 0 to 80. But I want to practice the algebra, get the revenue. If your revenue is wrong, everything's going to be wrong. Then do stationary singular endpoints. And at the end of the day, you're going to tell me how many coupons should we do and what will my revenue be with that number of coupons. So let's take a minute just to make sure our algebra is correct. If you do 400 times 1,000, you get 400,000. 400 times 20 would be 8,000x. Negative 5,000 times negative 5x times 1,000 is negative 5,000x. Negative 5x times 20x would be negative 100x squared. And so if I clean that up, your revenue, and if I put it in order, would be negative 100x squared plus 3,000x plus 400,000. So we got to make sure that our revenue is simplified correctly, and then we can do stationary singular endpoints. Sure, I have 3,000x there. I think I said 3,000, but wrote down 300. 3,000x. Thank you. So stationary would be, we take the derivative, which would be negative 200x plus 3000 equals 0. Then I would subtract 3000, negative 200x equals negative 3000, divide by negative 200, divide by negative 200. What do you get for x? 15 coupons, 15 coupons, okay? As far as singular, negative 200x plus 3000, there's no dividing, nothing going on, no singular on that point. And then endpoints, we were given 2, 0, and 80. But again, it's generally not the extremes. It's possible, just not likely. So we're going to plug those into our revenue and see which one gives us the most money. 15 coupons, no coupons, or 80 coupons. Okay, so I'm going to go to my calculator. I'm going to plug in the new revenue. Again, we can always graph it and check it. I'm just not doing all of them, but that would be negative 100x squared plus 3000x plus 400,000. And if we produce or give out 15 coupons, we would have a revenue of a lot of money, 400, a little more space there. We would make a revenue of $422,500. If we don't do any coupons at all, we're still going to make money. We'd make 400,000. Or if we give out all the coupons we have, which we can produce up to 80, we would make a revenue of 0. Probably not a good idea. So should we produce coupons, yes or no? Yes, and how many? So to maximize profit, let me type this out for you. To maximize revenue, you should create 15 coupons for a max revenue of $422,500. So it is worth it to make coupons, but we should only do about 15 of them. 15 of them. And this is how we figure out how many coupons. Should we do an incentive? If it's an event that you already have a lot of people and it's a high demand event, you wouldn't do any coupons. Coupons are used to stimulate and get more. And it shows that, yeah, it's worth it to get some more. Okay, now I know we've done a lot of word problems and your brain's probably going a little crazy right now, but I want to talk about one more. I'm not going to do it. We can do it another time, but I want to talk about one more word problem. And that word problem is in the review, and that's question number 9. Now, we're not going to do it, but I highly recommend that you do it. It's another word problem. Work on it. We can talk about it next class. But the idea is that you were given this formula, gives the oxygen consumption of in milliliters of a bird embryo from the time the egg is laid through the bird hatches in days. So basically, T is in days, O is oxygen. You graph it, practice that, and then it says, what's the oxygen consumption at day 20? Well, you just plug 20 in. So 20 goes into the original. But look at the keywords. Look at the keywords. So here, it says rate of change, rate of change. And then it says rate of change accelerating. Those are clue words that when you plug in 20, it's going to tell you the oxygen consumption. Rate of change is a clue to do what? Take the derivative. That's going to tell you how the oxygen is changing. What about accelerating? What is that tell you? Take the second derivative, how the rate of change is changing. So again, you'll work on it on your own, but when you work it out, you'll notice that 20 goes into the original. That tells you the oxygen consumption. When you take the derivative, that tells you how the oxygen consumption is changing. Now, when something's changing, it's not going to change that way all the time. The rate of change is also changing. That's when you take the second derivative, plug into that, and that tells you how the rate of change is changing. So the clue words are plug into the original, rate of change, first derivative, acceleration, second derivative. So real quick, an example of that is if I had the equation of driving somewhere, input, we'd have how many miles, output would be miles. If I took the derivative, that would be miles per hour. So yes, I'm going 100 miles, but how fast am I going? First derivative, I'm going 60 miles per hour. But am I going to go 60 miles per hour forever, the entire trip? No, the rate of change is changing. That's second derivative. So another application that's found in this chapter is second derivative, which is acceleration, how your rate of change is changing.